All right, today we're diving into one of the weirdest, most fascinating discoveries in all of modern physics. We're talking about the observation of a brand new phase of matter, something that scientists literally thought was impossible.
So let's just jump right in with a pretty wild question. Forget everything you know about crystals, like salt or diamonds. Physicists started asking something a lot stranger. What if time itself could form a crystal? What if the constant forward flow of time could just spontaneously break into a regular, repeating pattern? And, this isn't some sci-fi movie plot. We're talking about a real, actual state of matter that's been observed in a lab. It's got this perpetual, built-in rhythm that seriously challenges how we think about the fundamental laws of physics.
So what exactly is a time crystal? Well, at its heart, it's a system where all its parts, in this case atoms, are in constant motion forever. They're moving in this perfect, repeating pattern. But here's the really crazy part. They do it without using up any energy or giving any off. They just tick.
Okay, to really wrap our heads around this, we've got to start with something a bit more familiar. Let's think about a regular, everyday crystal that we see in space, like a snowflake. The key idea here is something called spontaneous symmetry breaking. Sounds complicated, I know, but the water to ice analogy is perfect. Think about liquid water. The molecules are all jumbled up, totally random. The water looks the same no matter where you look. But then you freeze it and bam, that uniform symmetry is broken. The molecules lock into this very specific, ordered, repeating pattern. They form a crystal.
So you can really see the difference here, right? On one hand, you have the liquid with its continuous symmetry. It's the same from any angle. On the other, the solid crystal has broken that symmetry into a discrete, structured pattern. And that jump from chaos to order, that's the crucial part to remember.
So of course, physicists took this idea and ran with it. They thought, hey, if a crystal can break symmetry in space, could something do the same thing but in time? And that's where they hit a brick wall, a really big one, that made the whole idea seem impossible for decades.
The question they were asking was, could you take this smooth, continuous flow of time and just break it, shatter it into this discrete, ticking pattern? Could a system just decide all on its own to start oscillating with its own rhythm and just keep doing it forever?
And at first, the answer from the universe was a big, fat no. The laws of thermodynamics just wouldn't allow it. Basically, a system that's all settled down at its lowest energy state, what we call thermal equilibrium, it can't just have parts moving forever. That would be a perpetual motion machine, and that's a huge no-no in physics. But, physicists, if there's a rule, they're going to look for a loophole. And boy, did they find a clever one that let them build this supposedly impossible crystal.
The solution was actually kind of simple, in a genius sort of way. They thought, okay, if time crystals can't exist when a system is stable and in equilibrium, well then let's not use a system in equilibrium. The breakthrough was to use something that's always being nudged and prodded from the outside, keeping it totally off balance.
This setup has a name. It's called a Floquet system. Just picture it. You take a quantum system and you just poke it over and over again with something like a laser. It never, ever gets a chance to relax and settle down. And in that constantly stirred up state, the old rules don't quite apply, and suddenly impossible things can start to happen. All right, so how do you actually build one of these things in a lab? Turns out there's a recipe, and it has 3 absolutely crucial ingredients. First up, you need the drive. That's your laser, the constant poke we just talked about. Second, and this part is super important, you need disorder. They basically blasted the atoms with random energy. Why? To keep the system from just absorbing all that laser energy, heating up and turning into a useless, chaotic mess. And finally, ingredient number 3, interactions. They made it so the atoms could talk to each other, so they could all get on the same page and lock into a rhythm together. And this is what it actually looked like in the lab. It's a chain of just 10 trapped ions. You can think of them like tiny little quantum spinning tops. And then scientists hit them with a whole bunch of precisely controlled lasers to apply that 3-part recipe, the drive, the disorder, and the interactions, over and over again.
Okay, so they built the thing, but how could they be sure it was a time crystal? Well, they were looking for a very specific, kind of weird signature in the results, the telltale sign that they'd actually made one.
And here it is, the smoking gun. So remember, the laser is poking the system at a regular interval. Let's just call that period T. Now, any normal system would just respond in time with the poke, every t. But a time crystal is different. It breaks that symmetry. It decides on its own rhythm. It only responds every other poke. So its period is 2t, exactly half the frequency of the drive. That stable, slower rhythm, that's the proof they were looking for.
This table really lays it out perfectly. It shows you why they needed all three ingredients. You see, with just the drive, the rhythm was all wobbly and unstable. Add in the disorder, it just got chaotic. But when you put all three together, drive, disorder, and interactions, bam! Everything locks into place, a stable, synchronized rhythm.
And you can see this right in the actual data. Look at what happens when you don't have all the ingredients. Each of those colored lines is a single atom, and, well, they're all over the place, right? It's a mess. The rhythms are sloppy, and the whole thing just fizzles out over time. Definitely not a time crystal.
But then, look at this. This is the money shot. As you go from left to right on these charts, they're cranking up the interactions between the atoms. And just watch. See how those colored lines, all those individual atoms, they stop their chaotic dance and just lock in. They lock into one single, perfect, stable rhythm. And look at the bottom charts. Their energy all focuses into one sharp spike right at half the frequency they're being pushed at. That's it. That is a discrete time crystal, born right there in the lab.
So, what's the big deal? Why should you care? Well, this isn't just some weird science experiment. This is the very first time we've ever seen a phase of matter that can only exist when it's being constantly pushed and prodded, far from its natural resting state. It literally opens up a whole new universe of physics we didn't even know was there to explore.
I mean, this really is a new frontier. It changes what we even mean when we say a phase of matter. Plus, it gives scientists this amazing new playground to study really complex quantum stuff. And if you look way down the road, who knows? This kind of super stable, built-in rhythm could be huge for building things like rock-solid quantum computers or flawless quantum memories.
And the scientists who discovered this said it best themselves. This isn't the end of the story, it's the beginning. It cracks open the door to a whole new field, searching for other weird and wonderful phases of matter that only show up when you shake things up a bit.
So that leaves us with this one kind of mind-blowing thought, right? Something that everyone thought was completely impossible was just created in a lab, all because a few scientists found a clever little loophole in the rules of the universe. It really makes you wonder, what else is out there that we think is impossible today, just waiting for someone to find the right trick to bring it to life?